And now, without further ado, Doina Precup from McGill University.
Thank you for the invitation to this workshop. I actually found the topic quite intriguing when I got the email. And then it got me thinking about, what can I possibly have to do with this topic? And so I decided to do a talk which will be partly a summary of work on temporal abstraction coming from the reinforcement learning community, and I'll try to stress and highlight the connections that temporal abstraction has with programs and some approaches that we use to learn these abstractions as programs. And I hope that perhaps this will generate some more ideas coming out of this very interesting and mixed community to push this work forward. So what's temporal abstraction? It's really a feature that's key to any kind of intelligence. We do it sort of seamlessly and effortlessly. So if you think of a very simple activity like cooking dinner, it involves all kinds of steps. Some of them are very detailed, like you have to stir some ingredients in a pot. And some of them are high level, like you have to think up what recipe, do I have the ingredients, how do I get the ingredients, and so on. So there's a mixture of timescales and representations that is needed to complete even a task that we think of as being fairly straightforward. And so we would like our intelligent systems to have this kind of ability as well. And of course, there's a long tradition both in classical AI and classical planning, as well as in control theory, to build these kinds of abstractions in various guises, sometimes as macro actions, sometimes as robotic controllers. I will give you today a flavor of this, which is sort of more specific to reinforcement learning. And just to say, there are actually several sort of alternative formulations of this in reinforcement learning. I will talk mainly about a specific one called options, which I've been involved with developing, but I will come back and point you to two other frameworks, MaxQ and hierarchical abstract machines, as we go along to sort of highlight the connections to programming. So what are options? You can think of options as behaviors that are trying to achieve some goal. And so we're going to specify these using three components. We're going to think of the agent as being in an environment where there are states. The agent can do some primitive actions. As a result of these actions, it can observe rewards, and it can observe transitions to the next state. And so now the option is going to be specified by saying, when can this be executed, how is it executed, and how does it terminate? Okay, so these are the three components. The first one, when can the option be executed, when can it be started, is called an initiation set. It's basically a function of the state. Then we have what's done during the option execution. That is called a policy. It's typically a mapping from the agent's observation or agent state into primitive actions. And then at the end, we're going to have a termination condition. Again, this is going to be typically conditioned on the observations or the state that the agent has. So throughout the talk, I'm going to use little omega for options, S denotes states, A denotes primitive actions, and R denotes rewards. So there's a very simple example there of what an option might be. If you have a robot in an environment and navigates this environment, then an initiation set might say, this option can initiate when the robot does not have anything immediately in front of it. Okay, this is a function of the robot's current sensation. The option might say, go forward. Okay, that's an internal policy. And when does it terminate? Well, it terminates when the robot has reached a desired position or when the robot has bumped into something. Okay, so that's the termination condition, which again is a function of the robot's observations and possibly other things, so I'm going to touch on that a little bit later. So this is a very well understood framework, quite widely used in the field. Now, what does this have to do with programs? So one way you can think of these options is essentially as programs that specify behaviors. And there's the most straightforward way to think about this is that we're going to use call and return execution. So we're going to call an option whenever the high-level controller, the high-level policy of the agent, decides to do so. The option identity then will be pushed on an execution stack. The internal policy is going to initiate, and that's essentially looking at some variables that we call the state, and doing an instruction, which I'm going to call an action. And at the end, we're going to have a condition that tells us how we terminate. Okay? Now, it turns out that you can also keep track of certain local variables inside the option. This is a particular formulation called semi-Markov options. So, for example, you might count time since you started and decide to terminate based on this time elapsed. Okay? So you could time out if you've gone for a long time and now you're bored of doing this option. Or you might have a function of the features that have been observed since the beginning of the option and accumulate those and terminate based on that. So we're allowed to have inside these local variables that we keep track of, whether you want to call them latent variables or just some kind of direct measurement of the trajectory. Both of those things are allowed. What we cannot do is remember things that are arbitrarily far in the past. So we're allowed to look at state. That was the summary we had at the beginning of the option. We're allowed to keep track of things inside, but not anything else. The other thing that we're allowed to do is call other options. So this is a model of hierarchical execution where I might initiate an action like the robot going to some particular goal. That might call an option that says go forward, which in turn might call an option which says go forward 1 centimeter and so on. This is all allowed, and it's handled as usual in programming by the execution staff. Now, there's an alternative execution model called interruption, which actually turns out to be quite useful in practice. Okay? And the idea here is that if we happen to observe that there is some better alternative to what the agent is doing now, we could sort of top-down say, okay, quit what you're doing now and switch to this other behavior. Okay? So this is like an interrupt in programming languages. It also has a well-defined semantics. In the MaxQ framework, it's called pooling execution. It can be done all the time, or it can be done only at certain times. And so it's if you want, a simple form of concurrency where there's sort of one other process that's allowed to interrupt what is going on, the behavior that's going on. The other thing I'd like to point out is that the option identity is actually a form of memory. So when we sort of reason about what's going on, we remember the state, and the option identity is on the execution stack. Okay? Now, this is not a memory of the past, of what we've seen in the past, but it's actually a memory of what it is that we're trying to achieve, what it is that we're trying to do. So you can think of this sort of more generally, not as the identity of the option, but some kind of a description, perhaps a latent variable description of what we're trying to achieve. This is very similar in flavor to things like universal value functions from Tom Shaw and colleagues, also with a very nice work that was presented earlier this week by Theas Kulkarni and colleagues. So in these alternative formalisms, we can also view sort of the temporal abstractions as programs. It's just that these programs are specified in a different way. So in options, we have these sort of mappings from variables to instructions. In the MaxQ framework developed by Tom Dietrich, you have, in some sense, a graphical programming language where you specify a graph of tasks and subtasks, and these will still ultimately have sort of little programs associated with them. In the hierarchy of abstract machines work developed by Ron Parr, you have little automata that specify these behaviors, and these automata are allowed to branch out into other little automata. And in fact, the work of David Andre a while back has sort of shown that you can build very explicitly variations of programming languages, for example Lisp, in order to be able to specify which of these are known in advance and given by the designer of the system, and which of these could be learned. And so there's an example there taken from his paper from, I believe, NIPS 2001, looking at a little environment, it's a navigation environment, and showing these little programs that he builds that specify what is going on inside of each controllers, and again, we can learn parts of these things. So what I told you so far essentially has to do with syntax. Okay, how do we specify behavior and what's the execution model? But as we know from programming languages, you also need semantics in order for things to be well defined. Semantics tells you how to reason about these programs and make sure that they're well behaved and well defined. And so in our case, what gives us the semantics is models of options, and specifically these are going to be predictive models. Because we're doing reinforcement learning, there's two kinds of things we need to keep track of. The second one will be more familiar to people who are used to programming languages. Basically, we need to know what happens when the program terminates. What is true when the program terminates? That's a kind of post-condition. Okay? So this kind of post-condition is the state at termination. And we would also like to know, ideally, how long the program took to execute. This is specifically because in reinforcement learning, we care about duration because it tells us what's the right way to discount the future or to balance the rewards received in the future versus those received right away. And so the transition model of an option essentially gives you this quantity. Because we're in a stochastic environment, it cannot be precise. It has to be a probability distribution. In our case, we model this using a sub-probability distribution that essentially gives you jointly the expected next state as well as the duration that it will take to get to the state at the end of the execution. The other quantity that we need, because of reinforcement learning, is the reward. Okay? And that's because reward is what drives the behavior. All policies and value functions are learned in order to maximize this reward. And so the other component that we keep track of is the expected reward during the execution of the program. And so you can think of these models as being predictions of the future, but as it turns out, they actually obey compositionality rules that are very similar to compositionality rules that you might have in usual programming languages. Okay? So, for example, if we want to reason about a regular programming program, you think, what's true at the beginning, what's the precondition? If that holds, what's the postcondition, what's true at the end? And then what does that let me call, and what will be true at the end of that? Okay, so that's a process called sequencing. So similarly in the options framework, you can think of sequencing these models by reasoning about what happens during the first option, what will be true at the end, that means what state will I have at the end, and then what will be true for the second option, the reward and its prediction, and so on. And those little equations there essentially give you, in closed form for the linear case, the relationships that govern this kind of sequencing. So if we have options and models and they obey these laws, then we can say our programs are well-defined. Okay, now in what sense are they well-defined? Well, they're useful for doing planning, and they will not produce spurious results during planning. And in reinforcement learning, the specific form of planning we're interested in is planning but driven by Bellman equations. The other thing that we might want to have is stochastic choice. So we might want to consider, if there are multiple options, which one do we want to do and take them with certain probabilities, and similar laws that are sort of very obvious govern the models in these cases. Now, there's actually a very nice paper a few years back by David Silver and Kamil Chosak, which looked at constructing options sort of compositionally by constructing these models, applying these rules. They play a little algebra trick in order to make these equations a little bit more compact, and then essentially they generate programs that solve towers of Hanoi, and they show very nice transfer between different sizes of these problems. Okay, so we have options. Options are programs. They have syntax, they have semantics. What this allows us is now to reason about how we might utilize these. And several pieces of work done a while back have shown that if you have a Markov decision process, it's a typical assumption in reinforcement learning, and you introduce a set of options in there, you obtain what's called a semi-Markov decision process. So what this means is you have states, you have transitions between states, but these transitions take variable amounts of time. Those amounts of time are drawn from probability distributions. Markov property means that this duration and where you end up only depend on the state when you started the transition and nothing before that. So that's the Markov aspect of it. The nice aspect of having this theory is that essentially all of the learning and planning algorithms from the reinforcement learning community that have been developed in the context of having actions transfer directly. Okay? So another way to think about this is that you can reason at the level of these temporal abstractions. You can reason about these programs, you can predict what they will do, and you can compute estimated values that can be obtained during their execution, which is quite nice because now we can think of sort of going back to the original reinforcement learning goal to generate good behavior and obtain that automatically. The advantage is that planning and learning can be much faster. These are very old results, essentially showing that if you have a system where you're doing planning, simple navigation task, you have a goal here. If you're doing planning at the level of simple primitive actions, then you get values that diffuse very, very slowly, one step at a time. Whereas if you have options and their models, then you can actually diffuse values very fast and obtain sort of a good behavior throughout the environment very quickly. So this is something that you would expect from sort of work that's been done in AI and control theory. In this case, the options were given. Okay, so there's a programmer who thinks about the problem, breaks up the problem down, writes the programs. Okay, parts of those programs could be learned. For example, the internal policies we can learn incrementally using reinforcement learning methods. But essentially, the designer specifies the system. There are actually more interesting incremental ways of doing this, okay, in a more haphazard fashion, but which still helps. So this is work published last year in which we tried to essentially just specify random subgoals and then have little deterministic policies that reach those subgoals that are solved in a very quick fashion. And then what the system does is it plans to sort of hop from landmark to landmark or subgoal to subgoal. And these results here are essentially showing you how much better you can do if you have these things compared to having just primitive actions. So an agent that has just primitive actions kind of stuck in its corner because it just can't see far enough ahead, okay? Whereas an agent that has these temporal abstractions sort of hopping to little pad to little pad and eventually reaches the goal. It's not perfect by any means, okay, because these programs are random and they don't give you straight trajectories, and you've eliminated the possibility of going back to primitive actions, but the planning is much faster and gives you an acceptable solution pretty quickly. Now, what is the difference between options and other ways of doing temporal abstraction? As I showed you, there's many different formalisms. They all have this kind of program interpretation. Essentially, the thing that we gain by thinking about options is an ability to sort of open the box of the program and look inside and reason inside about what's going on in a way that is very similar to what is going on in usual reinforcement learning. So an option has a Markovian structure. Inside of the option, we have little actions. The model of the option essentially is a kind of value function. The details here are not important, but I'm putting up the equations just to give you a flavor of this. And so the models can be computed sort of recursively, incrementally through reinforcement learning style updates, which is actually nice because it gives us a way to learn these things through methods that we're familiar with and to bring to bear all the power of current existing reinforcement learning algorithms to acquire these models. The other thing that we can do is learn about many of these in parallel. So if you're imagining that you have an agent doing call and return execution, there's a sequence of little subroutines that actually get called, but these depend on the states that are observed. And they also depend on how the designer has specified the high-level control policy. We would like to be able to learn about many different alternative ways of behaving from the same stream of data. That's called intra-option learning, and the structure of the options actually allows you to do that. And in particular, what we can do is think, whenever we observe an actual transition in the world, a state, a little action, a reward in the next state, we can think, what are all the options and models that are consistent with this transition, that could have done this transition, and update all of them at the same time. And again, the details don't matter, but there's a well-understood way of doing this. And it can be done with function approximation, Sometimes it involves important sampling in order to correct for differences in distribution, but there is a whole literature essentially on how to do this incrementally. So we have programs, we can specify them, we can write them by hand, they might be generated randomly, okay? That still doesn't tell us what's a good set of programs. And that is sort of where the frontier is. It's a problem that we've grappled with for 15 years now, and I think we finally have a pretty good answer to that. And so I will show you that very quickly in my remaining time. So basically we have a representation discovery problem. I would like to learn from scratch a good set of programs, a good set of options that can solve a problem. And so there's a few goals that we had in developing this work. One is that we wanted an optimization objective that is clear and that we can solve through principled means. We wanted to be able to handle both discrete and continuous state variables, action variables, and have continual learning of these programs as the agent progresses, and make sure that we make progress even within a task. And this is actually the problem that's plagued the community most of all. Many people have come up with option construction algorithms that work in the transfer setting where you have multiple tasks that you have to solve, but they would slow down learning and planning within a single task. And so we want to move away from that. And so the way that we built this algorithm is using a framework which handles both continuous and discrete and does continual learning and all these things, called Actor Critic. Actor Critic is a standard sort of way of thinking about optimization in reinforcement learning, where you have the environment and then you have a value function which is called a critic, estimating the value of different possibilities. And you have an actor, which is a parameterized policy. It receives gradients from the value function and it updates so that it takes more often the actions that are beneficial. So we have a very similar kind of setup here, where we have an environment, we have a critic that contains a couple of different gadgets inside, and then we have an actor which contains the behavior policy. This is sort of the master program, and it contains the different options. These are the different subroutines that we have, and we're going to adjust them incrementally from data. So the details here are not important. There's some gradient adaptation theorems that tell us how to sort of modify the structure, the internal structure of the options. I will just tell you what the meaning of this is, because it's actually pretty neat what falls out these gradient theorems. One adjustment that we need to do is inside any option, we need to take more often the primitive steps that actually improve the estimated reward. Okay, so that is pretty clear. If an action leads to a better state, then you should take it more often. The second thing that falls out of this is that if you have a better choice than the current option, then you should actually shorten the current option to give you the opportunity to pick that better choice. If the current option is better, then you should actually lengthen it so that you keep going with it for a while. Okay, so this is the second gradient rule up there. It relies on something that will be familiar to reinforcement learning people, on the advantage function over these different options. So what do we get? I will just show you, because I'm short of time, I will just show you these results with nonlinear function approximation. So here we do Atari games with a DQN style architecture. This is the network over here, and you notice that we have one big network that learns at the same time the policies over options, the termination condition, the policies inside the option, all sort of end-to-end in a continual fashion. And DQN is used for the value function over the options. This is the architecture of the actor. We have here 4 different environments. It's a little bit hard to see the DQN line, but we basically do slightly worse than Miss Bachman, better in Sequest, Zaxxon, and Asterix. And the interesting thing is that the performance is better within a single task. So we've achieved the goal of actually getting this representation to work better within a single task rather than in a transfer learning setting. The other interesting thing is that the options that result, even though they're learned through gradient descent, actually have pretty interesting semantics. So I'm showing here qualitative results. The top is from this Room's World Navigation task, in this task, many people have considered hallways as being good termination conditions for these options, because if you get to a hallway, you can navigate to a whole other area of state space. What you can see here, these light colors, is that indeed terminations are more likely around hallways, even though this was not really specified in the description of the problem at all. This was just, the agent was just asked to optimize for. In Sequest, we learned these options where essentially the agent has one option for going up to the surface, has another option for going down, and it switches between these two based on its situation. So in conclusion, I would like you to think of temporal abstraction as a way of specifying behavioral programs. There's syntax and semantics that goes along with that. And we now have efficient ways of learning these abstractions. There's a lot of stuff still to do. One of the things that I'm quite interested in, and I think would be good to think about, is other execution models. So right now we have call and return and we have interruption, but we know in programming languages we have many other things. We have threaded execution, for example. There is no way to do threaded execution exactly in the options framework, and I feel like that would be a very welcome extension. So I'll stop there and take questions.
So we're lucky enough that we have a working microphone. Questions?
Hi. Google Translation recently have some interesting results showing that you can either have a model for every language pair or have a single model for all language pairs by just having a special token indicating the language. Would that be possible for this? Like you have one model for all options?
Yes, so if we look at, I sort of skipped over the details, but basically when we parameterize these options, we parameterize them through sets of parameters, and these can actually be shared among all the options. So you have one way to structure the architecture where you have separate approximators for each option and its models and so on, and you can have essentially the identity or the description of the option being specified as an input to an architecture that has completely shared parameters, and that would be equivalent to the case you mentioned.
So, related question. In programs, we have function calls which take arguments, and the argument structure is very structured, right? And of course, you can do sharing of parameters in the option framework, but is there work on more structured sharing mechanisms?
So the closest thing to that is ALISP, really, this language I mentioned from David Andre, where he does have, so his functions take arguments, and those arguments can be typed, and so you can have this kind of structure. In the options framework, this is not necessary, but the state itself, right? So I didn't tell you what the state is, right? The state could be a vector mush, or it could actually be structured and made of components, like in factored representations, for example, and in that case, you would recover the same kind of structure. Not typically done.
So one more question.
Thank you for the talk. How do you choose how many options to have? And is there a big variance in the results depending on the number of options?
That's a very good question. So in the experiments that I'm showing, we are choosing the number of options. This affects computation more than the quality of the solution. If you have too few options, then you'll have bad solutions. But otherwise, it's basically the more you have, the more computation you're going to need to spend. What we are working on right now is actually providing not a discrete set of options, but a latent variable representation of the options, in which case this question will become irrelevant. But that's work in progress, so I can't really talk about it yet.
Okay, so in the interest of sticking to the schedule, if you have any additional questions, please save them for later. And let's thank the speaker. And next we have Rob Fergus from Facebook AI Research and New York University.
Okay, so I do apologize, I've actually changed the title of my talk from what was listed in the program. So I'm going to talk about essentially two topics, sort of learning how to communicate and also learning abstractions with neural nets. And this is really work done very much by Saina, who's a PhD student with me at NYU, and Arthur Schlamp, who's a research scientist at Facebook. Okay, so yeah, so I'm going to talk about two things. So the first thing will be about how to get neural nets to communicate with one another to solve complicated collaborative tasks. And then the second part I'll talk, which is very much the ongoing preliminary work, is really about sort of hierarchical reinforcement learning, closely related to what Doina talked about just now. Okay, so the first thing I'm going to talk about is this thing we introduced called a ComNet. So this is a communication neural network, and the idea is it takes as input a set of, it could be a set of data points, it could be a set of agents, as we'll see. And the idea is we're going to have a separate processing stream. It's going to be a distributed processing model that will essentially, so each element in the set will have its own stream. And we're going to provide a continuous communication channel between these different streams, okay? And it's going to be up to the models, up to each element to learn, essentially, up to each stream really, to learn how to communicate to solve the task. So just to give a little picture, so the idea is we have, in this case, we have a set here of, I guess, 4 different streams. The running vertically, that's one stream, and we have a series of communication cycles between the different streams. That's what you're seeing, the hop 1 and hop 2. And each stream is going to be modeled by a little neural net. That's what the green boxes are. So that could be a multi-level ceptron, it could be an RNN or something like that. And what we're going to do is at each communication hop, we're going to sort of propagate the hidden state. So that's the blue arrows. We're also going to have this communication channel that allows the different streams to chat with one another. So that's the red arrows. And the communication protocol the communication setup is going to be very simple. So it's going to be this broadcast channel. Okay, so what we're going to do is simply take all the messages that get sent from each, the hidden states from each of the different streams. We're going to average them and then pass them back to each agent. Okay, so in other words, you can see the equation just there. So essentially each agent is going to receive this communication vector C, which is going to be the average of all the other agents from the previous communication step. And the advantage of this is it's all sort of very simple sort of assembly, so we can train this whole thing with backprop. Okay? And the other sort of important things to note are that we're sort of invariant to the number of different streams we have, okay, because we're averaging that communication vector. So if that number, if it changes, if we change the number of streams, then the sort of the scale of that communication vector will remain the same. And also we're invariant to the ordering. There's nothing here that forces any explicit ordering on the different streams. Okay, so that, just to look inside one of those modules, that's the green boxes. So essentially there's going to be 2 inputs. There's going to be the hidden state from the previous communication step, and there's going to be this communication vector C. And all we're going to do is just have, simply multiply them by some learned parameters, H and C, big H and big C, pass them through a nonlinearity to give us an update on the hidden state. Now, the parameters are going to be tied across the different streams. So each of the different streams is going to use the same parameters at a given communication step. Okay, but we will have different parameters at different communication steps. So you can see the superscript I on the H and the C. So you can think about this model essentially actually as just one giant model. So if you, you can just take one layer of communication within it, you can effectively rewrite this as just taking, the hidden states of all the different streams. You can concatenate them into one big long vector, and you've got a big sort of transition matrix T that essentially has on the diagonal just a matrix H which propagates the hidden state, and then this communication channel, this averaging mechanism is just really a sort of series of block matrices off diagonal that will sort of just propagate the hidden state to the other agents. And so I just want to just take a step back and compare this to sort of the other the existing models we have. So if you think about a lot of the models like neural Turing machines and things like memory networks, these things which people use for program induction, essentially you have a sort of separate memory module and a controller mechanism. So you have this kind of explicit controller which will access the memory and do things to it. So in this ComNet model, it's all distributed now. Okay, so you have this sort of parallel processing. So there's no centralized controller, and essentially the things you can think about in memory are going to be each element in memory is going to have its own stream, and they can just chat with one another to achieve a given task. So just to illustrate that, you can think about a sort of task like the BABI tasks, which is widely used. So this is where you have to do simple sort of question and answering. You have different types of things like logical induction, like temporal reasoning and stuff like that. And so in this, we would apply this communication net in the following way. So essentially each sentence will have a continuous embedding, like a bag of words or something for each sentence in the little story. And that will, each sentence will have its own processing stream. And what's going to happen is essentially those processing streams will have to chat amongst themselves. So the sentences are going to discuss amongst themselves essentially what the answer to the question should be. So in this little example here, we've got sort of 2 communication steps, and then the instates of each sentence are going to be then concatenated, summed together and then passed to a softmax to produce the single word, which was hopefully the correct answer to the question. And in BABI, we supervised, so we have the ground truth answer to each question, so we can backpropagate an error signal through the different communication steps, updating the matrices in the communication net. And so you also have to, of course, provide the question, because it has to know what thing it's supposed to be answering, so that's also threaded in, essentially, at the input to the model as well. So this is a sort of slightly different way of thinking about addressing the task with the sort of existing methods, but it works actually almost as well as the sort of standard approaches. So we didn't sort of tune the model particularly at all for this, but you can see it does about as well as an end-to-end memory network. It's not quite as good as some of the state-of-the-art things, and yeah, I'm sorry, there's a more recent paper, I guess, from Yang Kun that actually has even lower error rates and things like that on these different tasks. But I think, so one thing we have been using for, and it's perhaps a more natural fit, is multi-agent reinforcement learning. So the idea here is that each stream now is really going to be an agent, so the state of each agent will be the input, and then the agents will sort of chat amongst themselves, and then the output at each time step will be essentially a discrete action for each agent. Okay, and then so the agent's effectively going to have to collaborate to solve a particular task. And then we can have a sort of outer loop here of some reinforcement learning algorithms. The one we use is reinforce, and that will sort of take a reward from the environment and present it. And we can use that then to sort of backpropagate through the communication net to learn how the communication should occur. So one task we applied it to was essentially this 4-way traffic junction. So you can think about this is a road. You have cars coming in. Each car is one of the coloured circles. And the cars are on fixed routes, so they can either go straight ahead, turn left, or turn right. And they're driving in a fog, so there's limited visibility around each agent. And if they, without naively, they're just going to crash into one another, okay, because of this fog. And they have 2 actions they can take. Go forward, so hit the gas, go forward 1 step, or do nothing, which is hit the brake. And so the idea is that the agents, though, even though they can't see very much, they do have this communication channel available to them. Okay, so they can actually chat amongst themselves to decide, whether they should advance or stay put. And so what we're going to see is sort of we're going to show some examples where we have a sort of very variable number of agents. So the number of cars on this junction is going to vary with time. We're going to have a sort of big negative reward if the cars collide with one another, and we'll have a small negative reward just to penalize each time step, just to make sure that the cars try to get through the junction quickly. Okay, so let me play this video. It's going. Okay. So what you're seeing is, initially before training, of course, the policies of each agent is completely random. So there's all kinds of collisions. That's what you're seeing with the X's, and so you can see the collision count in the bottom right. So of course it's complete mayhem on the road junction at the moment. Nothing. Everyone's crashing into everybody else. And then you can see after training, the cars have figured out a way to sort of chat amongst themselves. And you can see that there's basically no collisions. When you see the flash, that's when the car's putting on the brake to slow itself down to avoid a collision. And you can see that it's able to solve this task. And this is, that's a fairly simple, relatively simple one. You can think of more ambitious ones where you have, 4 junctions and a load more cars. And you'll notice that the number of cars is changing dynamically here, right? So each time step you can get a different number of cars, but because the communication protocol is kind of, invariant to the number of agents, the whole setup still works. And you can see after training, the thing is, very smooth and there's no collisions. So just to show some, quantitative results for this. So on the plot on the left, you can see we're varying the visibility. That's the sort of visibility of the environment around each agent. And then on the y-axis, we're showing the failure rate. So failure is essentially if you have any collision during an episode. And you can see that if you just don't have any communication, that's what the independent one is, then it's complete mayhem when you have this one-by-one visibility, when you can only just see the current position you're at, nothing else. But then if you allow the model to communicate, that's the red curve, then you can see it actually does pretty well. It certainly does, very low failure rates when you have a little bit of extra environment visibility. And the other sort of things we also tried, so look at the table, we also tried just using a discrete communication, so we force it to use a discrete symbol. So it turns out that at least for these little experiments, that didn't work quite as well. So the numbers here of failure rates are lower is better. And then we also tried just having one big monolithic model. So what happens if you just have a giant fully connected net that just mapped the states of all agents to their actions each time step, and so that doesn't work so well either. And you can also try varying the little module you use, whether you're using a multi-level perceptron or an RNN, and by and large, it doesn't make a huge amount of difference, but you can see, the approach works with those two. So one thing you might wonder is, how exactly these agents communicating with one another. So one thing we did was to go in and do PCA on those communication vectors. So they're obviously high-dimensional things. We can just project them down to 2 dimensions. And what you see is that most of them are sort of fairly small energy. They're quite close to 0. And you see a few clusters of quite large magnitude. And you might say, well, okay, so maybe some of the agents have just sort of died and they're just using a kind of 0 hidden state and they're not doing anything interesting. So what we also did was to, plot out the hidden state for the agents as well, and the colors are corresponding, okay? So you can see that for the green blob on the left, so for those when the communication vectors are 0, if you look on the right, you can see typically the hidden vectors are not 0, okay? So what you see, in fact, is that the agents have learned they might carry significant information in their hidden state, but by and large, they don't tend to, say much on the communication channel very often, okay? And so it sort of makes sense, because if you have this broadcast channel, if everybody's shouting at once, then no one can actually hear anything, and it doesn't actually, it's not going to contain any information. So by and large, you see that the agents keep quiet, and occasionally they make a strong, say something clearly, and that's what you're seeing this sort of almost discrete tokens that have, discrete, communications that of communication vectors that have been learned. So the next question is, what are these clusters? So what we can do is we can go in and probe, what each of these, from one cluster, what do these communication vectors do exactly in terms of behavior of the agents? So for example, if we take one of these clusters, like say the one labeled A, if you go in and look closely over many different episodes, what you'll see is that when one of the cars, or one of the agents reaches a certain location, indicated by the blue circle, it essentially puts this communication vector onto the channel, and all the other cars at the locations indicated in red stop. Okay, so it's effectively like saying, hey, I'm coming through the junction, can you guys just put the brakes on because I'm going to come through? And similarly, you see, the other communication vectors, correspond to sort of the cars coming from different directions and so on. Okay, so it's learned something sort of sensible about how to achieve this quite complicated task. So we also applied to a few other things, like you can imagine a sort of very toy version of StarCraft or something like that. So you have a bunch of enemy bots, and then you have a bunch of troops. In this case, we have 5 of them, and they just shoot at each other, and they have health and stuff like that. So you can essentially, the naive strategy would just be to shoot, at the sort of nearest enemy bot. But there are sort of smart things you can do, like sort of gang up. They can concentrate fire on the weakest enemy and things like that. So you can effectively, by communicating amongst themselves, they should be able to sort of improve their win rate against the sort of naive enemy. So this is just sort of trying to show that effect. So we have in this case here we gave the enemies a little bit of an advantage. So the default win rate is actually below 50%. The numbers here are sort of win rate versus the enemy averaged over many episodes. And what you see is that if you allow the model to communicate, it does better than not communicating. So the top row is no communication between the different troops, and if they get out to chat with one another, then they can do better. And you can also try sort of more agents in the game and so on and so forth, and the story is somewhat consistent. Just to discuss some related work, so actually there's obviously big literature in the reinforcement learning world with multi-agents, and typically though the communication protocol is kind of fixed. The people specified how the agents should chat to one another. So what's different about this work is we're sort of learning that. And actually this is really very much the same idea as some concurrent work at NIPS from Oxford, from Nando de Freitas and others, where they're essentially using looking at riddles, like how you can have agents chatting amongst themselves to solve little sort of riddle puzzles and things like that. Okay, so our thing is, they're also using continuous communication like we are. You can also actually think about our model as a kind of form of graph neural net. Okay, so each agent is going to be a vertex in this graph, and the communication vectors that are being sent are effectively like the messages that are passed on the edges of the graph. And of course, you can have a sort of dynamic. Each time step, you can have a different graph structure, and that will correspond to sort of agents entering and leaving the environment. Yeah, I guess this is like one sort of practical instantiation of this idea. Okay, so just to summarize, this is what I've talked about here really is a kind of distributed neural net model. So it's suitable when you have tasks where the input is effectively a set, and perhaps the output could also be a set too, or it could just be a single output. And the models are actually able to learn this kind of sparse communication protocol from scratch, and you can use it for sort of in reinforcement learning for these multi-agent problems. So yeah, so this was actually a paper that was at NIPS this year, and then we also have code online now if you guys want to play around with it. Okay, so that's the first thing I was going to talk about. And the second thing, which is, I should really emphasize, is very much preliminary work, as you'll see. So this is really about learning abstraction with neural nets. And so what I'm really referring to here is hierarchical reinforcement learning. So as we heard from Doina, she's motivating this idea as well. You have complicated tasks, say like going to work. There are thousands of different actions. You'd really like to be able to sort of automatically learn sensible sort of subtasks, like getting to the station, taking a train, walking to the office, and so on. And then, that would seem a sort of more efficient way to kind of plan and do things. And so obviously there's a whole bunch of people thinking about this problem, and particularly recently there's a whole slew of recent papers in the area. So I'm just going to talk about sort of one very simple approach to doing this, which is to basically have a kind of recursive form of policy. So just to describe the idea in a little bit more detail. So in a standard reinforcement learning, you have a policy which takes an observation of your current state and maps that to an action. So what we're going to do in this is to change that slightly so that now the agents also get to perceive the task. So the task will have some sort of representation. It will be a vector that will sort of essentially indicate what kind of task we're dealing with. And the policy will just essentially take that as an input. Okay, so now we'll produce an action based on both the state observation and the task at hand. And so of course we're going to be dealing with situations where we have a whole bunch of different tasks in each, in different episodes and so on. And so that we want a single policy that's going to be able to handle all these different tasks. And so, in general, the task will be an embedding vector, but in this, we haven't got quite as far as more general representations. So as I'll describe. So just to show you a picture of the overall setup, you can think of, if you look at the top box in blue, that's essentially your standard policy. So you have an observation that comes in, but you will have some task representation now, which will be another input. And then the policy is going to output an action, so it has two types of actions. So it has actions in the world, and if it outputs one of those, then the agent just goes ahead and executes that action. But it also has a second type of action, which is really to output another subtask. Okay, so in this case, if it does that, effectively what's happening is you're going to sort of pop down a level, you're going to recurse a level, and then we're going to use the same policy as before. So it's essentially a copy of the policy. Now the only difference is now that instead of having the original task as an input, the subtask will now be the input. Okay, so I'm looking at this thing here. So essentially, we're conditioning now on a different task at hand, and then the policy there can output an action in the environment, and it also has the ability to potentially recurse again, although in this preliminary work we're only recursing one level, and it also has a termination action as well, in which case it'll sort of pop back up to the top level, and then you're sort of back at the flat model again. So just to sort of, this is the sort of pseudocode, I guess, of the whole thing, so that the setup here has, you have state and then S, and you have some list of potential task IDs G, and we do keep track of time inside this, so you want to have the maximum time perhaps for the episode, and there are three sort of potential possibilities, right? So you either, as I say, you either take an action in your environment, either you terminate and pop up to the next level in the recursion, or you recurse down. So if you recurse down, then you're basically going to take your action, copy it over to this G variable, and then just call the whole thing again. Now, to encourage the model to actually use the recursion, because in some sense the top level has access to all the actions in the environment anyway, so why would it bother to do the recursion? So to encourage it a little bit, we do give some small internal reward for using recursion, and we do actually slowly increase it. We start with it being 0, and we slowly increase it throughout training. Okay, so that is a subtle form of supervision that we do introduce. Okay, so just to talk about the related work for a moment, So there's obviously the idea of options has been around for a long time. We just heard from Doina about the option critic stuff. So I guess in ours differs slightly in the sense that our options are sort of anchored or grounded in some sense in these subtasks. So we do have sort of specified subtasks that will form our options, whereas I guess in Doina's thing it's more general. It can learn whatever it wants to do for each option. And then there have been several papers that just were submitted to iClear. So there's ones from Bushmi Colley and Honak Lee and others, where they were essentially using maze-based to look at sort of hierarchical RL type problems. And I guess in that paper they were sort of doing this a two-stage training. So they were sort of training initially on the subtasks, and then once they've got those under control, then they would train some sort of meta control on top. Okay, so I guess, yeah, the difference in this work is we're trying to do everything a little bit more unsupervised. We're trying not to give explicit supervision about what's a subtask and what isn't. And then, yeah, there's also another paper from Sergey Levine, Dan Klein, and Andreas. So they were also looking at modular RL. So in this case, though, they were giving sort of policy sketches. So they were specifying for sort of complicated tasks a little bit what the sort of composition of the subtasks is. But we like the tasks they used a great deal. So they actually had the sort of Minecraft-based tasks that we're going to use, as you'll see in just a second. And then I should also mention there's an interesting work from Dawn Song and her students showing for sort of program induction how recursion is super important if you're using, she was using neural program interpreters. But recursion, she's using multiple levels of recursion, we're just using one. Okay, so just in terms of the task representation, we would ideally like to have a sort of completely arbitrary vector, for example, that would encode natural language. We haven't quite got that working yet. So in fact what we're going to do is just have a sort of one-hot vector indicating the idea of the task at hand. Now during training what we're going to do is just throw in the tasks in any random order. Okay, so the model's just going to be given complicated tasks, easy tasks, just at random. What will happen, we'll see, is that effectively the model will learn initially the fairly easy tasks to start with, and then it will start using those easy tasks to sort of solve the harder ones. Okay, so we're not providing a specific curriculum at all here, we're just throwing the things in and the model's going to learn. So just to show the task at hand, basically we have it's going to be this sort of Minecraft type thing. We're going to grab different items, those are the sort of easy ones as it were, and then you have crafting ones, we have to grab items and then go to a certain location. And the model's not told which ones are easy or hard. We don't specify for the more complicated ones, 4, 5, 6, 7, what this subtask composition is. So it just has to figure that out for itself. And we use sort of maze-based as the environment. We just use a pretty simple control, policy, just 2 hidden layers. It's trained with reinforce, and we do have, just a reward for completing the task and some penalty for each time step. So just to show a little bit of the evolution during training, so you can see that the grabbing tasks, which are easy ones, it figures out those pretty quickly, and once it's got the hang of those, it can then it's able to actually figure out the making tasks, which obviously you can't do if it doesn't know how to pick up objects in the first place, which sort of makes sense. And you can see it sort of using the recursion, so initially it's completely random, so it doesn't know whether to use recursion or not, and then it figures out it doesn't need the recursion for the grab tasks, but then for the more complicated making tasks, you can see it figures out it needs to use recursion for those. And then if you try comparing to a smaller, non-recursive model, you can see that these graphs are a little bit misleading. The y-axes are quite different scale. So on the left, without recursion, it really doesn't work very well at all on these more complicated make tasks. But if you have this recursion in place, then it's able to succeed fairly well. I should say, however, that if you have a bigger model, these tasks are so simple. In fact, you can still solve them with the model without recursion. But I think as we make the task more complicated, hopefully, the recursion would be vital for success. Okay, so I'm just going to show you a little movie of the whole thing, the trained model. So what we're seeing here, and just pause this for a second. So you're seeing that red blob is the agent. In the top right, you see the overall goal. In this case, it's to make an axe. And you can see the subtask is underneath. Okay, so this is the subtask, which is to pick up the metal, and then if I decide to play, you'll see it achieving that. And you can see in the bottom right, I've just given a little key for the different tasks. So it's figured out how to sort of go pick up the items and then go to the appropriate crafting table to actually build the thing. So just to finish up, so this is obviously very much preliminary work. We're basically trying to do focus here on trying to have a minimal amount of supervision in when we learn the subtasks and so on. And we're just trying to basically use the simple sort of recursive idea with the policy. So obviously we're looking to sort of add more levels of hierarchy, to add more complicated tasks and so on. And I think we'd like to also get to the point where the task specification is just in natural language rather than anything else, rather than just a discrete task specification. Okay, so I'm out of time, so I'll stop there.
So we've got some time for questions.
A very simple question. So 1% collision rate seems to be very high for a self-driving car. Do you know what's happening over there?
So that's 1%, I guess, over the entire episode. It fails. I mean, so Simon.
It's actually physically impossible to remove all collision because cars are forcibly entering to the junction. So they don't, just push forcibly them. So
one car runs into the back of another, it's
Yeah.
just entered.
sometimes that happens.
Why did you choose the averaging function for the communication?
Right, so we wanted something that would be invariant to the number of agents. So that's one option. I mean, it's true we could have done sort of geometric average or something like that. I think we chose it also because it's the simplest, and it actually turned out to work just fine. I mean, we did have plans to try more complicated, approaches to combining the vectors, but it actually seemed to work fine. So as you can see, I mean, it has this nice property that because you're doing something dumb like averaging, most of the agents have to actually keep quiet if it's the models to work at all. So I think that's kind of interesting.
I was wondering, like, how would you preserve identity of, like, if you have like 100 agents all like talking to each other, and if you average it, then you can't tell who's talking to who.
Right, but they have their own hidden state, right? So each agent can sort of keep that around. I mean, it can store its identity in its hidden state.
But then when you average it,
but each agent gets its own hidden state from the previous time step as well as the communication vector, right?
Yeah.
But the point is, so I see what you're saying. You're saying so that, if agent 2 can't tell agent 3 next door to it that it's going on,
Yeah, because everyone gets the same signal.
Yes, it's true. I guess, right. I mean, we did do some experiments where we had local communication, so we actually would enforce it like the car junction, go and talk to cars nearby, and it does help a bit. Okay. So that sort of speaks to the point you're making. So you do see improvement there.
Okay, thanks.
So I saw there was like a 10% error rate when there was a 1x1 visibility. So I was just wondering, like, how big is the shared vector state bus? Like, could they learn to communicate, like, agent 1 says its location in the first byte of the bus, agent 2 says location in the second byte, so they all know where they all are, and what does each agent know? Does each agent know its exact coordinates, or does it just know?
It does. Each agent knows its coordinates, right? Right. So there's 10 cars. I mean, I think it's about 50D. Is that right? So. Okay.
So in the bigger simulation, there's about 20 cars, and the number of dimension of the communication vector is around 50. So it's going to be really hard to all of the agents to put their location. Even if they want, they don't have explicit ordering on them, so they don't know which bit to use. And we've seen it from the PCA upload that mostly actually they're silent. So if you're past the junction, you don't have to actually. You're not going to collide with anyone, so you don't have to communicate.
So, last question.
That's in relation to the previous question back there, 2 questions ago. One interesting model maybe for you guys to try would be to have like a blogging model, where each agent writes to, say, a limited, so it's a limited resource like the web, so then it can decide whether to write a message or not. And then each agent then can decide what to read from what other agent, so like with an attention model.
Sure. So what's the overall task be? I mean, you're trying. What are the agents trying to do?
So that would overcome this issue of agent identity and being able to. Yeah. Then it would matter who you listen to.
Yeah, right.
And you could create beautiful task like.
So we did actually. There reminds me, we did actually have an attention vector on the communication thing at some point, didn't we? We tried it. I think it. So I mean, yeah. I mean, admittedly for these problems anyway, we didn't seem to need it. But yeah, okay. For the thing you're describing, yeah, you would need it. Yeah.
Okay. So let's thank the speaker. The next speaker is Percy Liang from Stanford University.
Okay, great. All right. Thanks for the organization inviting me and everyone for being here. So this talk's going to be a little bit different, and the title is a little bit mysterious. So what do I mean by the title? This is a large program. It's, I guess, parts of the Linux kernel. And in general, the question of how humans are able to just write millions and billions of lines of code kind of amazes me. And most of it actually kind of works. But if you look at kind of where state of program induction is, and this is kind of a brief survey of some of the stuff that mostly kind of from the programming languages community. So Sumiko Wani had something on Flashfill, which is actually deployed in Microsoft Excel a few years ago on end-user programs. So if you have a situation where you have a bunch of emails and people are translating them into names, then you might want to induce a little short program like this that actually fills in the rest of the columns. Here's another example from Mondo, which is if you wanted to synthesize a larger program, it might be too hard to do so, so you sketch out kind of a template and then you fill in some of the holes, kind of like what A-List was doing that Doina pointed out. Or here's another example on stochastic super optimization. So the idea is that you want to induce a program that multiplies the numbers in assembly, and on the left is this program that was compiled through GCC, and Stoke, which is this work out of Stanford that was able to induce a program which was much shorter and actually faster. And so there's actually some work here also on super optimization by Schmidt and colleagues. And what's notable here is that these programs are actually induced kind of from scratch via some actually very simple NCMC. But the question is kind of how do we scale up? And in some sense, all of these kind of previous cases run into these combinatorial explosion really, really quickly. So just as a kind of to set expectations, I'm not going to talk about how to actually get there. This is kind of a far-reaching goal. What I'm going to talk about is kind of initial steps and ideas that might lead us in the right direction. Okay, so two ideas are kind of modularity and thinking about kind of specifications, which I'll talk about. Okay, so this is actually work from 6 years ago that I appeared at ICML. And the idea is that suppose you induce a program that computes a minimum of 2 numbers. Okay, so then you come to another task and you're asked to induce the maximum. It should be kind of easier, right? So this is kind of the learning multitask learning that many people have been talking about. And the observation is that programs often share kind of common substructure. But if you look at these 2 programs, what makes it kind of annoying is that the part that changes, which is this little operation, is deeply embedded. And so what is a subprogram? Well, maybe it's stuff out around it, but then the fact that you have variable names also makes it kind of hard to extract subprograms meaningfully because you might just have unbound variables, which makes no sense. So what we did in this work was to try to create a new representation of programs which was kind of easier to model. And the idea is based on an extension of combinatorial logic from way back. And instead of representing a program with, for example, this is the tree of x squared plus 1, we're going to use these combinators b, c, and s, and I that specify how the argument to this function should be kind of routed down the tree. Okay? And so now, based on this representation, subprograms are simply subtrees. Every subprogram is just a subtree. Everything is kind of has this uniform quality to it. So in this language, here would be the representations of min and max, so don't expect, I mean, you can read this as kind of if x is less than y, then x otherwise y, but don't worry about the details. So now that subprograms are subtrees, we can actually define a prior over a program. So we decided to use one based on adapter grammars. And this is kind of a generative story that describes how to generate a sequence of programs which are related. So you have a cache of kind of basic programs that you've generated so far, and if you're trying to generate a program of a particular type, you either generate a random kind of a base case combinator of the type, or you recurse, or with some probability you just fetch something out of the cache and you return it. Okay, so the cache is the thing that kind of puts high probability on having lots of programs that share common substructures. Okay, so now when you want to do program induction, you condition on the XY pairs that you get in your data, and then you do MCMC. So I'm not going to go over the details, but some experiments, we looked at these text adding tasks where input is a string and output is a string which is changed somehow. And we show that basically by having this joint prior, you do a lot better than if you have kind of independent priors or uniform priors. Okay, so I just want to kind of highlight this kind of idea of using modularity. The basic idea is that if you want to induce one program, you should be able to leverage what you've learned about other programs. But the main challenge is how do you parameterize this kind of sharing? The way we did it was to expose these shared programs as subtrees. And what's kind of the general model has kind of a natural interpretation. As you kind of write more and more code using your general model, you keep this cache of library of useful primitives that you can kind of reuse again. Okay? All right, so that's a quick overview of the modularity aspect. So after this work, I felt like something was kind of missing. And what was missing was, if you think about how we write programs, right? Suppose you show up on the job one day and your boss tells you, as a developer, and boss tells you, well, write a program that takes these as inputs and produces these as outputs. This would be kind of an awful way to specify the behavior of a program, right? Instead, you should probably the boss would tell you sum of squares of primes in the list or something like this, and which is kind of really easy to now the task becomes a lot easier. So the observation is that people write code not by doing combinatorial search over programs, but really from these partial specifications. And maybe some demonstrations of code as well, but the partial specification actually seems quite important if you want to scale up to have large programs. So I'm going to talk about partial specifications in the context of natural language because that's the kind of a natural way to describe code. So here's an example. So suppose you wanted to write a program that computed the largest city in Europe by population. So what would this look like? Well, there's cities. Let's say cities returns a set of cities. There's something about Europe. Let's take the things that are contained in Europe, intersect these things, and then compute the argmax by population. Okay, so this is semantic parsing is a task of taking these natural language sentences and converting them into a program that you can execute and you can produce the answer. Okay, so this can be used for various question answering. You can also use it for kind of other types of non-question answering tasks like executing actions on. But in general, the idea, the paradigm is that you have some sentence describing what you want. It doesn't have to be formal, it's in natural language, but that's going to guide the search over programs. And now once you have a program, you can execute it. Okay, so there's a long history of kind of semantic parsing in natural language processing, and recently there's been kind of an increased interest. One of the things that we've been kind of trying to push is scaling up semantic parsing to larger domains such as freebase or even kind of semi-structured data. And in these domains where you have lots of kind of complexities and lots of primitives, things become kind of more challenging. So just to give you a kind of an idea of what this kind of task looks like. So this is a table from Wikipedia about the sprinter Piotr, and suppose we wanted to induce a program that corresponded to answering in what city did Piotr's first place finish occur. Okay, so what kind of computation is this encoding? Well, this is encoding something about looking at the position column, selecting the elements that are first, selecting the last one, going to the row, and then finally selecting the venue. Okay, so this is the type of typical example from the data set where you're given natural language and you want to induce a program that can go operate on the table to produce the answer. Okay, so this data set consists of about 20,000 question and answers, a number of tables, and we designed this data set in some sense to be kind of challenging, logically challenging, so the programs are not kind of simple lookup, but involve various types of arithmetic operations, comparing, taking argmax, conjunction, disjunction, and added to that complexity is that the tables are unnormalized, which means that we have to kind of figure out how to maybe even look inside a cell to compute the answer. Okay, so we solve this task as follows. So here we have a table, we convert it to a graph representation for convenience. Here's a sentence, and here's an answer, so these are what training examples look like. And we want to somehow figure out what the program is, such that the program captures the semantics of the natural language, but also outputs something that matches the answer. So the way we go about doing this is as follows. For every example, we can generate programs recursively of increasing size by generating length 1 programs, length 2 programs, all the way to length, I guess, k programs until we find something that gets the right answer. And then the training is a standard kind of maximum likelihood training where we maximize the probability of getting the right answer given the question, where we marginalize out the program. So we generate all the programs, this forms the elements of this terms of the summation, and then we can marginalize this out using the stochastic gradient. And what's inside this model, I'll talk about later. All right, so some results. So if you just try to naively predict, train a classifier that predicts which of the cell entries is the right answer, then you do fairly poorly. With the semantic parser that we trained, we got 37.1. Recently, Arvin, neural programmer, got 37.2, so we have to one-up us a little bit, but basically it doesn't matter because these results are still low enough that they're going to improve quite a bit, hopefully. So what are kind of the errors that the system is making? So it turns out that there's actually kind of a lot of unhandled things. Like when you see words like consecutive, they look innocuous, right? But if you try to kind of expand it out into a logical form, this actually requires a bit of work to compute. Same with the word same. And like I said before, the tables are normalized, so if you have this question, how long does this show last? And the table says the string 2 p.m. to 3 p.m. Now we have to convert these into times and subtract to actually figure out the answer. So this is a little bit of trickiness, and the way we're generating the programs, we're, I guess, I didn't say this explicitly, but we're not generating all the programs because that would be too large. We're using some sort of beam search to prune as we go along, and therefore we're not generating everything every time. So we found this quite frustrating, right? So what we're doing is we're searching over the set of programs, and thousands of logical forms later, we might or might not get the right one. So this is really kind of a classic kind of program induction problem of finding these needles in a haystack. If someone tells you the answer is 5, well, how do you know how to actually compute the number 5? So what we decided to focus on is what I call oracle accuracy. And the question is, how often can the system even generate a set of, let's say, 200 counter programs that contains the right answer? I'm not asking for the system to spit out the right answer as kind of ranked number 1. I just say, you can give 200 possibilities, and let's see how many of the examples you can get right if I use the oracle to choose which of the 200 is the right one. And the answer turns out to be 76. Okay, so, you know, our accuracy, remember, is 37, 76, which means that, I guess, you know, it seems like, you know, 76 isn't too bad. But it turns out that, you know, there's a kind of more more things going on. So there are, suppose you have this question, how many times did Greece hold the Summer Olympics? And the table is about Greece, so you can ignore Summer Olympics. So here's the correct program. You count the number of rows that Greece occurs, and that gives you 2. But there's also other programs. You count the number of times Norway holds the Olympics, you subtract that, which just happens to be 0. You also get the right answer. Here's a crazy one that, you know, you look at some row, and then you, I guess, which is, the Greece held the first Olympics, so you go to the first row, and then you go 2 down, and then you look at the index, and that also gives you 2. So when you do the program induction, it turns out that there's tons and tons of ways of just getting the right answer for wrong reasons. Okay, so if you look at how many of the 76% were actually generating the right program, well, it's only 53. So that's a little bit less, which means that 50% of the time, we're not even able to get the right program. Okay, so what we decided to do about this, before that, just a kind of a note, is that kind of recovering the correct programs in this setting, at least, is in some sense an unsupervised program, because you only get information about what the right answer is. No one tells you what the right program is. But getting the right program actually seems kind of, you know, important, because if you get the wrong program, then you're going to generalize in a crazy way later. Okay, so the challenge that we decided to do is, can we actually generate all programs up to some size that produces the correct answer? So remember, there's this exponential search space that we have to deal with. So how are we going to generate all programs? So in this case, it would be generating, given this sentence and this answer, how can we generate all the programs that evaluate to 2 and have, let's say, Greece in it? So at this point, we don't actually have a semantic parser that understands language. So the key intuition, so this is an HCL paper from this year, is dynamic programming. And if you have 2 programs, one that computes the population of the capital of Colorado and one that computes the population of the largest city in Colorado, then you should be able to kind of collapse these into the basically kind of equivalence class, because this program basically, these all execute the same thing. And if you try to build on top of this program, then the only thing that matters is kind of the denotation of this program. So hopefully you can kind of save some effort. Okay, so the way we implement this is, given the sentence and the answer, we're going to compute all of the reachable denotation. So we construct programs that I can reach Colorado. I can generate Colorado. I can get to Denver by either taking the capital or a larger city. I can also get to the United States. I can also get the population. I can get a bunch of different things. But I only keep track of kind of one way to reach each of these denotations. I don't keep track of all the possible ways. And then the second step is now we can discard all the denotations that don't reach the correct answer. So United States can be discarded because it has nothing to do with any logical form that computes, I guess, the population, which is 649,000. Okay, so this actually reduces, eliminates about 99% of the denotations. And then on the remaining denotations, then we can kind of go and enumerate all the programs on the remaining denotation. We don't have to enumerate them because we have a compact, dynamic programming representation of all the programs that actually evaluate to a given answer. So I should note that, of course, this relies on the number of denotations being, small. And this plot shows that compared to the number of programs or logical forms, as you increase the size of the program, this is blowing up really fast, whereas the number of denotations is much smaller. Of course, the number of denotations is actually going up exponentially as well, but just kind of at a much slower rate. And this was kind of enough to, since we stop at a kind of 8, this is enough to kind of make everything kind of tractable. Okay, so how do we actually do? So these plots show that as you increase the beam size or you generate more and more programs, how many, what is the oracle accuracy? Which is meaning how many of the examples can this number of this number of programs kind of cover the correct program. Okay, so the beam search basically was what we were doing before, gets around I guess 53, remember? And now using this dynamic programming approach, we're up to 76. And the remaining, it's kind of a long tail of various things. Some of the tables are kind of messy, there's some noise, but I imagine that kind of the ceiling is probably the 80s or something. But this is kind of a big improvement. So one other thing that you can do with this is now we have sentences and we have all the logical forms that get to kind of the right answer. Now we look over the entire data set and we can kind of go kind of mining for macros. So what I'm doing here is showing that whenever the string, the same number of, occurs in a sentence, I look at kind of the program fragments that show up most often. And this, I guess it's a little bit hard to read, but this basically encodes the program that captures, the abstract program that captures sing. And this captures how many more. You can see that there's a kind of subtraction here. So what this is really kind of doing is, it's kind of similar to options if you want to think about natural language words as kind of highlighting these kind of abstract procedures which are reusable, because you can say how many more cars, how many more cows, and it's kind of the same logical form piece that fits in. Okay, so our ongoing work, we're trying to use these in a semantic parser to actually improve the accuracy. Okay, so the summary of so far is that we're using semantic parsing as a way to convert this partial specification, aka natural language, to programs. And the key observation, which I guess I didn't highlight enough, is that once we've learned the language, meaning that all of you know natural language, and when you look at this, the programming task is very easy. So you don't have to search because you know what largest means. And in some sense, this is a way that humans are able to create these large programs because we kind of understand, oh, okay, natural, if you understand the specification, it's kind of rather easy to write things down. But the key point is that natural language understanding is actually a hard problem. So until we've kind of learned a model that actually can understand language, search is going to be hard, and what I presented is kind of a dynamic programming solution that relies on kind of modularity of program execution to produce the set of all consistent programs. Okay, so just final remarks. So this program, this workshop is about neural program induction, so where's all the neural stuff? So here's a slide of neural stuff. So we have this work that, so what I didn't mention is how you go from natural language to the programs. And this is where kind of the neural models come in. We use attention-based sequence models that just treat this as a sequence and output the logical form of the sequence. And the reason to do that, I guess, In the interest of time, I won't explain, but basically, this is actually a very tricky and complicated problem because language is annoying to deal with sometimes. But we can kind of learn this automatically. I'll skip the data recombination bit, but so the results on this were actually good. We got state-of-the-art results on this this task, and in some sense, it's kind of a simpler method because of sequence. Okay, so now you can ask, well, this was just neural models for producing the programs. Why not go all the way and say, let's just neuralize the execution as well? So here I want to kind of raise 2 points. One is that the idea of factorization. And you can think about, if you're answering a question, there's really factors into understanding the question and knowing the answer. So for example, what is the largest city in Missouri? You might not know the answer, maybe you do, but it doesn't matter. Anyone can kind of write down the logical form for this. And, but you have to probably know something about US geography to actually figure out what the answer is. And by doing this type of factorization, there's kind of this added strong generalization that happens where if I swap out the knowledge, in another world, maybe Kansas City was not the largest city in Missouri, I can still use this semantic parser to produce the kind of right answer. And for kind of the databases we're changing, this is kind of important. So point 2, which might be, is more speculative and maybe more controversial, is what is actually this differential execution buying you? It certainly seems to be interesting. And one thing it could buy you is soft reasoning, and it happens in language. And another thing it buys you is you don't have to do combinatorial search. But that's a little bit, I guess, yeah, it's true that you don't have to do combinatorial search, but now you have this huge non-convex optimization problem, so it's kind of like jumping out of a frying pan into a fire. But to the extent that it works, I think the reason, and this is now even more speculative, is that maybe it's kind of some sort of over-provisioning that's going on. Because once you have all these kind of hidden units, there's kind of multiple ways to kind of attempts at getting the right answer. So somehow the search is kind of built in. And this actually also happens in discrete search as well, when you have multiple registers. Okay, so I'm out of time, so I'll just summarize. There's 2 ideas, the modularity and kind of specifications. And maybe these are kind of ideas that eventually will lead us to be able to synthesize larger programs. So thanks.
So we have time for a quick question.
I like your point about which you may use a problem specification when writing V programs. But I wonder how would you deal with the case, say the specification is, say, write a program to do sorting or find the shortest path?
So how do you have a specification for sorting or shortest path?
When the specification is sorting, which didn't specify how to do the sorting.
I see, yeah. So I think, so if you take the kind of natural, so there's one answer which is that you actually want the algorithm to figure out the most efficient sorting algorithm. Maybe it's better than this. This actually does happen in program induction. But another answer is that maybe you have an idea of how you want to sort. So you want to say split down the middle and then sort recursively both sides. And if you write that in natural language, that could be valuable hints into guiding the search. To the extent that you can brute force small programs, then go ahead and do it. But if you want to synthesize large programs, then you need to provide some sort of structure. And it could be either through natural language or probably subprograms that you've induced previously.
Sorry, sadly we're out of time, and presumably a lot of people want to go and eat something. So let's thank the speaker again.